Chemistry, we're on to the next lesson in the Foundations unit. It's on a subject called Significant Figures and Measurements. So let's talk about rounding. You're probably familiar with this. Rounding is a process of limiting the number of digits after a decimal point. So example, round the following number to 3 significant figures, and we're going to talk about that in this lesson. So there you have the number 3.47658. So the 3 significant figures are the 3 to the left, 3.47. Now the next digit after that 7, after that last significant figure, is the rounding digit. So if the next digit to the right, the 6, is less than 5, then the 7 stays as a 7. You could think of it as rounding down to 7. It stays at 7. If that digit, the next digit, is 5 or greater, so if it is 5 or anything greater than 5, then the 7 is rounded up to an 8. Well, in this case, the 6 is 5 or greater, so that's going to round the 7 up to an 8, so the answer will be 3.48. Significant figures, which we simply refer to as Sig Fig, indicate the precision of a measurement. In math terms, they provide a set of rules for how many digits you should use in your answer based on the precision of your laboratory measurements. So here we have a room, and it has a length of 8.1 meters and a width of 5.2143 meters. So you measure the width of the room with a very precise laser device that is precise to 0.0001 meters. The length of the room you measure with an old meter stick, and you measure it less precisely, just to 8.1 meters. To obtain the area, you would use the formula that you use for the area of a rectangle, width times length. So it would be 8 times 1 times 5.2143, and what that would give you is an answer of 42.23583 square meters. So again, significant figures, Sig Fig, indicate the precision of a measurement. There's our room, and there's the area there down at the bottom. So this value of 42.23583 square meters indicates a level of precision for the measurement that is misleading, because the length measurement could have actually been anywhere between 8.05, which would have rounded up to 8.1 if you rounded it, and 8.14, which would have rounded down to 8.1. So that means that measure could have actually been anywhere between those two numbers. This means that if you multiplied those two numbers, 8.05 and 8.14, by the very precise width measurement of 5.2143, you could get an area that would range between 41.975 square meters and 42.444 square meters. So that's quite a variation in the range of the final answer. The rules of significant figures limit the number of digits you can use in this answer to 2. And so the answer is actually going to be 42 square meters. That's what you would actually report it as. And so what we're going to learn in this lesson is the rules that determine why that's 42, why that's a 2-digit answer. So here are the rules for significant figures. All non-zero digits are significant, with no exceptions. Zeros to the left of the leftmost non-zero digits are never significant. Zeros in between non-zero digits are always significant. Zeros to the right of the rightmost non-zero digits are significant if there is a decimal point, and not significant if there's not a decimal point. And 5, the final significant figure answer must have the same number of digits to the left of the decimal point as the calculator answer, with non-significant significant figure digits represented by zeros. So wow, that's a lot of rules. So let's just get into some examples, and they'll start to make sense. You have a copy of this in your reference sheet. So let's just take some examples. 326. There's 3 significant figures, so all non-zero digits are significant. By the way, the advantage of doing this on video is you can always pause the video and answer the questions yourself. I'm going to move kind of quickly, but once you see the question, pause it and see if you can answer for yourself. 3,045. Okay, you can pause and think about that for a second. I'm going to move on. How many significant figures? That has 4 significant figures. A 0 between non-zero digits is significant. How about this one? 3 significant figures. No decimal, so the trailing 0, the one on the right, is not significant or it is uncertain, but in this class we'll say not significant. This number? 5 significant figures, leading zeros. Those to the left of the 2 are never significant. 10,000. 1 significant figure. Trailing zeros are not significant or are uncertain if there's no decimal point. What about this number? 8 significant figures. All the zeros are significant, including the one on the far right, because there is a decimal point. This number? 4 significant figures. Leading zeros left of the 1 are not significant. Trailing zeros right of the 1 are significant because there is a decimal point. Let's work on multiplication. This is where you're going to see this the most and use significant figures the most in multiplications and divisions. So the numbers being multiplied are called multiplicands, and the answer is called a product. So the rule for multiplication is the product, the final answer, should contain the same number of significant figures as the multiplicand with the least number of significant figures. So let's go ahead and just look at examples. 2 times 4 is 8, so that's the calculator answer. How many significant figures would the answer be? It would also be 8. 2 and 4 have 1 significant figure, so the answer has 1 significant figure. 31 times 23 is 713. Now this one is tricky, and students miss this one. That would be 710. So they look at it and they say, well, there's only 2 significant figures in both of those multiplicand numbers, so the final answer can only have 2 significant figures, so that's going to be 71. But each of the multiplicands has 2 significant figures, so the answer is limited to 2 significant figures. The last digit, 3, should be rounded down. So this is Rule 5. If you go back to those rules, this is Rule 5. It says that the number of digits to the left of the decimal point, and there's an implied decimal point after 710, the number of digits has to be the same as the calculator answer. So the calculator answer has 3 digits, 7, 1, and 3, to the left of the implied decimal point. So that means the final answer, significant figure answer, has to have 3 digits, but it can only have 2 significant figures, so that third digit has to be a 0. So the answer is not 71, it's 710. Okay, these two numbers, what's the significant figure answer going to be of that calculator answer? Calculator answer is 0.3432. It's going to be 0.34. 0.104 and has 3 significant figures, and 3.3 has 2 significant figures, so the answer is limited to 2 significant figures. The answer is rounded down to 0.34. 314 and 0.204, there's the calculator answer. 64.1. Each of the multiplicands has 3 significant figures, so the answer is limited to 3 significant figures. The 5 rounds the 0 up to a 1. What about this? Again, this is going to be a little bit of a tricky one. Think about it. Okay, it's 40,000. So the 5 limits the answer to 1 significant figure, but there are 5 digits in the calculator answer, 42735. That means the significant figure answer has to have 5 digits, but only one of them can be significant. So you add the 4 zeros and you don't add a decimal point, otherwise they would all be significant. Okay, so the 2 is rounded down to 0 and all remaining digits are zeros. This one, 0.0010. The 0.10 in the multiplicand limits the answer to 2 significant figures. The 4 is rounded down to a 0 at the end of the calculator answer, and the 1 and trailing 0 are the only significant figures. This one, 42. The measurement example on the earlier slide at the beginning. The 8.1 limits the answer to 2 significant figures. The 2 after the decimal is rounded down. Now we do divisions. They're done the same way. 1.2. The 2 digits in the denominator set the answer at 2 significant figures. What about this one? 3.4. 3,400 has no decimal and is 2 significant figures. 987 is 3 significant figures, so the answer has 2 significant figures. This one, 200. 0.8 is 1 significant answer, so only the 2 in the final answer is significant. The 3 rounds the 2 down, so it stays as a 2. In other words, that 2 in the very beginning. There is no decimal in the final answer, making the 00 not significant. Okay, so again, you have 2, 3, 4. You have 3 digits to the left of the decimal in the calculator answer. So you're going to have 3 digits to the left of the decimal in a significant figure answer. And since the Sig Fig answer can only have 1 significant figure, those other 2 digits are going to have to be zeros. All of the digits to the right of the decimal can just be eliminated. They go away. The rules for addition and subtraction are different. They're completely different than the multiplication and division rules. So let's look at those. Rules for addition and subtraction. You line up the decimals, which is what you always have to do when you add or subtract decimal numbers. The Sig Figs are determined by the number with the least number of digits after the decimal place. So again, let's just get into an example. So you're going to add these 2 numbers together. So the number with the least number of digits after the decimal is the 23.45. So you just draw a line right beside that. Now you add the numbers, and you get 29.186. The only significant figures are the 4 to the left, 2, 9, 1, 8. Those are the 4 significant figures. However, the 6 is going to be your rounding digit, and it's going to round that 8 up to a 9. So 6 rounds the 8 up to a 9. The final answer is 29.19. Now let's do a combination problem of multiplication and addition subtraction. So use PEMDAS, that stands for parentheses, exponents, multiplication, division, addition, subtraction. That's called the order of operations. And you keep track of the significant figures, but you do not round until the end of the problem. Okay, practically truncating, you can cut off some digits. In other words, if you get a calculator answer that's 10 digits long, you know it's not going to be that many significant figures. You can chop off some of those digits. Just use your judgment. And assign the correct Sig Fig at the end of the problem. So here we go. We'll do one. So 3.24 times 1.021 plus 12.1. So PEMDAS says do the multiplication first. When you multiply those 2 numbers together, you get 3.30804, but it's limited to 3 significant figures because of the 3.24. But you don't do anything to that number yet. The 3.30804, you don't do anything to it yet. Now you're going to take that number and add it to 12.1. It's up in the original problem. And when you do that, you get 15.40804. So the only 3 significant figures that addition can have is the 1, 5.4, and the 0 that's just to the right of the red line keeps the 4 at a 4. It does not round it up to a 5. So both steps 1 and 2 limit the answer to 3 significant figures. So you have to take the one that has the least number. In this case, they're both 3, so there's no conflict. So the final answer is going to be 15.4. Let's do another example. Compute the following. You see the numbers there. So again, you do the multiplication first. 3 times 0.451 equals 1.353. That's what your calculator would give you. So that's only one significant figure, though, because of the 3 in the multiplicand. But you don't round it yet. So now you take that number and you add it to 6.02. Draw the line beside the 6.02 because that's the one with the least number of digits. And now you just go ahead and add. And you get 7.37. Those are the 3 significant figures. And then you have a 3 to the right. So the 3 rounds the 7 down, so it will remain as 7.37. Now, step 1 says you can only have one significant figure. Step 2 says you can have 3 significant figures, so your final answer can only have one significant figure. It's the least of the number of significant figures of those 2 steps. So the addition produces 3 sig fig, but the multiplication limits the answer to 1 sig fig. So your final answer is simply going to be 7. You can eliminate all the digits after the decimal place. Okay, this next one is the rules for logarithms. You'll probably never see that in this class where you have to do this, but let's cover it just to complete the topic. So you count the number of significant figures in the number from which the log is being taken. That's called the argument. This is the number of digits that should be in the after the decimal. That's the key. After the decimal in the log, and that's called the mantissa. So we're going to take the log of 12.43, so that has 4 significant figures, and that will give you the calculator answer, that long number you see right there. So since the 12.43 has 4 significant figures, there will be 4 digits after the decimal place in the final answer, so it will be 1.094, and that last digit gets rounded up to a 5, so you have 4 digits after the decimal place in the final answer. Okay, now we're going to go to a quick lesson of distance measurements. You're actually going to do this more extensively in the lab, where you're going to actually do some measurements. But let's talk about measurements and how you read measurements, because this works in tandem. It works together with significant figures to determine how many digits are in a final answer. So the distance. So the ruler below shows the metric units on top, centimeters, and imperial English units on the bottom, inches. We pretty much never use inches, feet, yards, the type that we use here in the United States, the imperial units. We're always going to be dealing in metric, and that would be centimeters. So that's 1 centimeter on a ruler, what you see there indicated. In chemistry, we do all measurements in metric units. The number of units on the top are centimeters. The small lines between each centimeter is a millimeter. So there are 100 centimeters in a meter. There are 1,000 of those tiny little lines, 1,000 millimeters in a meter. And you'll see meter sticks laying around the classroom. There are 100 centimeters and 1,000 millimeters in a meter. Okay, so let's do some readings here. So the measure is exactly on the 4 centimeter line. So the way you would read that is a millimeter is 1/10 of a centimeter. It's 0.1 centimeters. So that's 4, and then you have to express the number of millimeters. So that's in this case 0, because it's exactly 4 centimeters. Now, that's how many digits you can actually read based on the lines on that ruler. You're allowed to guess 1 additional digit. In other words, if you think that that number is in between 2 of those little tiny lines, the millimeter line, you can estimate, that's an estimate digit, what you think that number is. So let's read this. Millimeters represent a precision of 0.1 centimeters. So you can definitely see 4 point something. 4.1, 4.2, 4.3, 4.0, 4.9. You can definitely see that. In addition, the measure is allowed to estimate 1 more decimal place. This allows the measurement to be 2 places after the decimal place. So a correct reading on this, it's not a matter of your choice. A correct reading on this ruler or this meter stick has to be 2 places after the decimal. So if you think it's exactly on 4, then it would be 4.0, and then your estimate digit, that last 0, would be a 0 if you think it's exactly on 4. Let's look at some other examples. Here's 6.7. So you look at that and you think that that arrow is pointing exactly to 6 plus 7 of the little tiny lines, the millimeters. So that's 6.7. Now if you think it's exactly on the 7, that 7th little line, then your estimate digit would be 0. So it would be 6.70. It has to be 2 places after the decimal. 10.25. So you think that it's at 10, you think it's right about at the 2, but it's somewhere between the 2 and the 3. And you think it's halfway between the 2 and the 3. So that would be 10.2, which you can see the 2 line, the 0.2 line, and then you think it's a little past that, maybe halfway, then you would say 5. 10.25, again, 2 places after the decimal. and 12.38. So that measure is definitely past the 12. And you count 1, 2, 3 of those little lines, but you think, oh, it's almost to the fourth little line, but not quite. So you might estimate that as 12.38. Liquids form what appears as a disc on the top, and we'll talk about chemically why that happens, but for right now we're just interested in the measurement. This disc is called a meniscus. You can see it there. It actually seems to have a thickness to it. The height of the liquid is measured from the bottom of the meniscus. So the meniscus, the volume, measure the volume at the bottom of the meniscus where you see that arrow pointing. Each of the small lines is a milliliter, which equals a cubic centimeter. So milliliter and cubic centimeter are the same. So how would you read this? This is called a burette. We're going to use it for titrations in this class. So you can see 21 milliliters, 22 milliliters. Each of those are a milliliter. Now you can see markings, 10 markings in between 21 and 22. So where that arrow is pointing is right about 21.3. You'd count down from the 21 towards the 22. So it's 21.3 milliliters. Now you still have to do your estimate digit. If you think that meniscus is a little bit past 21, then you might say 21.31. If you think it's exactly on that third line right there, then it would be 21.30. So with a burette, you have to be 2 places after the decimal. A triple beam balance is used to measure mass. You're going to use that quite a bit in this class. The illustration below shows the beams on the triple beam balance. The center beam is in increments of 100 grams. That's the biggest, the heaviest. They put it in the middle because they don't want the device to tip over. And the top beam is in increments of 10 grams. You can see that 10, 20, 30. And the bottom beam is in increments of grams. The smallest, though, the smallest lines you see on that bottom beam are 1/10 of a gram. So you can read to 1/10 to 0.1 grams. So the reading on this scale to the right would be 536.80. Let's look at why. You take the 500, you add 30, and then down at the bottom beam you see a 6, and you see the line, as best you can see with this resolution, is at about the 8. So that's the precision you can read based on the lines. Now you still get an estimate digit. So the 0 is the estimate digit. The resolution of the image is not clear enough to tell where the point lies between 8 and 9. So let's just say it's right on 8, then it would be 0.80. Time is measured in the same way in any system, same units in any system, seconds, minutes, and hours. That would be clock time. And then calendar time, days, weeks, months, years. And in chemistry you could do that if you're studying geologic processes, chemical reactions of geological process. It could be very long amounts of time. Oh, and there's century as well. Alright, so that takes care of this lesson on measurements and significant figures. You're going to see how we use the two of them together to correctly express the number of digits that should be in the answer of a scientific calculation.